Chapter 29, Alternating Currents. After this chapter, you should be able to do these things. First one, measure frequency and voltage using a cathode-ray oscilloscope. You have already learned this in the O-level class. They gave you a picture of the screen of the cathode-ray oscilloscope and asked you to find the period, the frequency, the voltage. So we will see that in this lesson also. Describe an alternating current or voltage in terms of period, frequency, peak value. You know, peak value means the highest value. Peak value and r.m.s value. So r.m.s, root mean square value. We can have a look at that over here. You can see the frequency here. You can see I0, that is I think it's given here, okay, the peak value. I0 is known as the peak value of the alternating current found from the highest point on the graph. Okay, so you can see here 2 and -2. We will see the details afterwards. And here V0 is the peak value of the voltage. So when you see this naught, that is the peak value. We have also used it for amplitude. Okay, x0 in maybe in other chapters or for mathematics you would have learned x is the displacement, x0 is the maximum displacement, which is the amplitude. Under simple harmonic motion, for mathematics you would have learned it. Okay, then we also had the root mean square. You can have a look at that. You can see this here, root mean square value. Whatever is in the green boxes in this textbook is very important. You have to know what it is and you have to memorize the definition with understanding. So for example, over here they have told you what the root mean square speed is, okay, sorry, root mean square value is. Now you have also learned about root mean square speed in a previous chapter in AS. You learned about root mean square speed. Now this is again you have root mean square, but this applies to the current. The root mean square value of an alternating current is that steady current which delivers the same average power as the AC to a resistive load. We will learn the details later. You have to memorize this definition with understanding. Alright, so root mean square. Okay, relate r.m.s and peak value for sinusoidal current. You know the shape of the sine curve or the cosine curve, so that is sinusoidal. Now previously when we looked at the current, you saw that the graph is the shape of the sine wave graph. That's why we call this sinusoidal current. So alternating current, it goes from positive to negative, negative to positive, so that means the electron moves forwards, backwards, forwards, backwards. Therefore we get a alternating current, and here we have that as a sinusoidal current. You saw that in the graph as a sinusoidal current. So AC current, or sorry, alternating current AC is sinusoidal. So r.m.s and peak values for sinusoidal currents. We already saw that peak value I showed you, and also r.m.s. We will see the details afterwards. Solve problems involving transformers. In the O-level classes, you had learned the equations for transformers. We assume that the transformer is 100% efficient. So the power input or the power in the primary coil is equal to the power output or the power in the secondary coil. So that was given by VI, power equals voltage times current. VP IP equals VS IS, P for primary, S for secondary. The primary coil is also called the input coil. The secondary coil is also called the output coil. And we also learned that the ratio of the voltages for the two coils is equal to the ratio of the turns. We got that equation and then we solved problems with that in the O-level class. So here also you will have something, you will have that also over here. Explain how diodes and capacitors can be used to produce rectified smooth currents and voltages. You have learned that rectification is the process where you convert alternating current to direct current, and the instrument or the device that does that is called a rectifier, converts alternating current to direct current. Alright, so here again are the topics: sinusoidal current, alternating voltage, power and alternating current. Why use alternating current for electricity supply? You know that the transformers won't work with direct current because there has to be a changing magnetic flux. The magnetic field has to keep changing for the transformer to work. That's why we use AC. With DC it won't work. Transformers, you have learned about step up and step down transformers. Step up transformers increase the voltage, step down transformers decrease the voltage. Rectification. And finally we have the summary and end of chapter questions, which you have to do all these. Let's go through the summary so that you can have an idea of what this chapter is about. That will make it easier for you to understand when I am explaining this chapter. So let's go through the summary also. So here you can see sinusoidal alternating current can be represented by this equation: I equals I naught sine omega t. Now this omega t should be in a bracket because that is the argument of this sign. So I equals I naught sine open bracket omega t close the bracket. This omega t, the sign applies to the whole thing, omega t. So you get the product omega times t, the product of that, and then take the sine value of that. And your calculator here has to be in radian mode. Keep that in mind because we are using omega. Okay, you have learned omega equals 2 pi f. So make sure your calculator is in radian mode when you use this sign over here. So this is the equation that you have to know. We will be using this equation. I naught is the peak value of the current, I is the current. Okay, so it's a sinusoidal alternating current. T is the time, omega. Okay, we will go into the details. Okay, angular, you have learned omega, you have seen omega before under circular motion, you called it angular speed. Now here we have angular omega, angular frequency. Okay, the root mean square value of an alternating current is that steady current which delivers the same average power as the alternating current to a resistive load for a sinusoidal alternating current. So we have r.m.s equals I naught divided by square root of 2. Again, you had seen this definition before. It was in that green box. I told you those definitions are important. Okay, here is another equation. So you have this equation and then you have this equation, and you can see r.m.s. r.m.s stands for root mean square. So root mean square value of an alternating current, that is this one. r.m.s is that steady current which delivers the same average power as the AC to a resistive load for a sinusoidal AC. Then electric power is usually transmitted at high voltages. This allows the current to be reduced, and so resistive losses are lower. Again, under power transmission in the O-level class, you learned that the certain step-up transformers are used to increase the voltage, so that the electric power can be transmitted with less power loss. You know the equation P equals VI, and to get this for the same amount of power, if you increase the voltage and if you reduce the current, you can get the same amount of power. But when the current is lower, the power loss in the cable is lower. Okay, so electric power is usually transmitted at high voltages. This allows the current to be reduced, and so resistive losses are lower. So you know the equation P equals VI. When you increase the voltage and if you decrease the current, you can get the same amount of power. So for the same amount of, to have the same amount of power, you can increase the voltage and reduce the current. Why we reduce the current? Because the higher the current, the more the collisions between those electrons and the metal ions in the wire, and as a result that will convert the energy, electrical energy, to thermal energy. So thermal energy is heat, so that's a waste of energy. That's why we reduce the current and increase the voltage, so that we can get the same amount of power and we can transmit it with less energy loss. And what happens is, once it comes to the receiving end, so we send it from the power station using a step-up transformer, we step up the voltage, and then when it comes to a certain neighborhood or a factory or near a school, we use a step-down transformer to reduce the voltage, because the voltage is very high. Again, we'll go into the details later because this is just the summary. Okay, transformers are used to change an alternating voltage. Now again, you can see the word alternating, because transformers won't work with direct current or direct voltage. So the voltage has to be changing. So if the current is changing, if it's alternating current, the voltage will also be alternating. The voltage is stepped up or down in proportion to the turns ratio of the transformer. That is what I told you before. You have learned this equation in the O-level class also. You can see the ratio of the voltages is equal to the ratio of the number of turns. S is the secondary coil, P is the primary coil. For the primary coil, again, N is the number of turns in the secondary coil. Here NP, this is NS. NP is the number of turns in the primary coil. So here we have voltage in the secondary coil, voltage in the primary coil, number of turns in the secondary coil, number of turns in the primary coil. And this is if the so we have this, and you can see the power in the primary coil is equal to the power in the secondary coil. Again, if you look at the diagram, you can see that here the input coil is the primary coil and the output coil here is the secondary coil. So the power in this is equal to the power in this, and the ratio of turns is equal to the ratio of the corresponding voltages. Alright. Diodes are used to convert AC to DC. You know, diode doesn't let current flow in one direction. Diode doesn't let current flow in both directions. It allows current to flow only in one direction. So using the diodes, we can convert alternating current to direct current. Alternating current is a current which flows forwards, backwards, forwards, backwards. So for half the time the current is flowing in one direction, for the another half the time it's flowing in the reverse direction. Okay, but in direct current it only flows in one direction. Diodes are used to convert AC to DC. A single diode gives halfway rectification. You had already seen this word rectification, and I told you what a rectifier is in the O-level class. Also you learned the word rectifier. It converts alternating current to direct current. Now if you have just one diode, you will have for half the time the current flowing in one direction, remaining half there is no current. That's why they say now, so you will get something like this. Now if you use one diode, for half the time the current will flow to the let's say to the right, and the remaining half time it will flow to the left. So when it tries to flow to the left, the diode doesn't let it flow. So for that time the current will be zero. Then again the current flows, let's say again to the right. So you will have this. Again it tries to flow to the left because it's alternating current, but the diode doesn't let the current flow in the reverse direction. So you'll have this. So this is called halfway rectification. And if you use four diodes like this, okay, we'll go through the summary again. A single diode gives halfway rectification. A bridge of 4 diodes gives full wave rectification. A capacitor smooths the rectified voltage. Then you can see this network of 4 diodes. Bridge of 4 diodes. So what happens is alternating current, right? So half the time the current is flowing, let's say like this, and it can't flow this way because you see the way the diode is connected, the diode doesn't let current flow this way, but this diode lets current flow this way. So the current flows in the direction of the arrow of the diode. You can see the arrow is this way. Here the arrowhead is this way. So it won't let current flow the other way. So it goes like this, goes through this, like this, like this, like this, goes through this, like this, and this. Now that is for half the time. The remaining half, the current flows the other way. So one time the current flows this way, the other time the current flows the other way. So let's see. So it goes like this, like this. Now it can't flow through this part, so it goes like this, like that. Again, it can't flow this way, so it goes like this, like this, like this, like this. See it, but what you can see is over here always the current flows down. See, no matter which direction the current flows, to the left or to the right, always it will flow in one direction over here. So using this bridge of 4 diodes, you convert alternating current to direct current. So this is working throughout. Okay, but when it's flowing this way, the current is flowing through this path. But when it's flowing the other way, the current is flowing through this path. But during the entire time, the current flows through the resistor in one direction. So here we have AC, but here we are getting, in this part, we are getting always DC. See, up to there. Again, from here all the way up to there, it's flowing in one direction. So what you see here is this, if you use one diode, but if you use a bridge of 4 diodes, you will get this. You see over here, the for half the time there was no current, but here during the entire time there is a current. Okay, so we are still in the summary, and also we learned you saw this capacitor smooths the rectified voltage. Now here the voltage is rectified, and that once you fit a capacitor, this is what happens. Something like this, a smooth rectified current. Okay, so we can see the details afterwards. Okay, let's go to the beginning of the chapter. I think we discussed a lot about the rectifier. Okay, so here this is what we were going through. Solve problems involving transformers. Explain the benefits of transmission of electrical energy at high voltages. Explain how diodes and capacitors can be used to produce rectified smooth currents and voltages. Explain how diodes and capacitors can be used to produce rectified smooth currents and voltages. Okay, so capacitor does this smoothing, the diode does the rectification, and we saw the graphs already. Okay, so then the first topic is about the sinusoidal current. I already explained that to you. So for half the time the current flows to the left, let's say, and half the time the current flows to the right. So you can see that over here in this graph, this is an alternating current, and it is, as a result, it is sinusoidal. So what happens is for 10 milliseconds it is flowing in one direction, say in the positive direction, maybe to the right or upwards, let's say. Then the remaining time it flows to the left or in the other direction, so in the reverse direction. So that's why you have this. So for the first 10 milliseconds it is flowing in one direction, for the next 10 seconds it is flowing in another direction. Again the process continues. Okay, so that's why it's called alternating. Okay, and I already explained to you the pattern. Alright, the graph has the same shape as the graphs used to represent simple harmonic motion. We already learned simple harmonic motion, it was chapter 19, and it can be interpreted in the same way. The electrons in a wire carrying alternating current thus moves back and forth with simple harmonic motion. So for one time the electron is moving to the right, and another time is moving to, so it moves back and forth, and that is also a simple harmonic motion. That's why we get this graph as a graph of something vibrating in simple harmonic motion. The electrons in a wire carrying alternating current thus move back and forth with simple harmonic motion. The current varies like a sine wave, and so it is described as sinusoidal. Okay. I think the other parts are okay. Then the equation I equals I naught sine omega t. When you learned about simple harmonic motion, also you had an equation like this for amplitude displacement x is equal to amplitude x naught sine omega t. Okay, again here we call this the angular frequency. In simple harmonic motion also you called it the angular frequency, but in circular motion you call the omega angular velocity or angular speed. Okay, so very important equation, and you can see omega equals 2 pi f. The unit of this omega is radians per second, same as the unit for the other places where you saw the omega, angular speed, angular velocity, angular frequency, the unit is still the same. Then this equation again you have seen it several times in the O-level class also. In the A-level class you saw this equation and this one, but in the O-level class you have seen this equation. Okay, you have to know what all these quantities are. I already explained it before. I naught is known as the peak value of the alternating current found from the highest point on the graph. It is the amplitude of the varying current. So I naught is the amplitude of this varying current. In this case it is 2. Okay, then there are questions to help you understand this better. Make sure you do answer all these questions. Now you can see this equation, just like the equation for simple harmonic motion, we can write it like this. So over here I equals I naught sine omega t. I naught is 5.0. You can see that. Compare this equation with this one. Okay, before the sign you have this. So this is I naught and omega is 120 pi. Okay, so in this question they are asking those. Then once you find omega, you can find f. Omega equals 2 pi f. F is equal to omega over 2 pi. So you know omega, you know, then you can find f. That's what they're asking you to do. So make sure you understand and is able to use these 3 equations. You will need that for this chapter. Okay, then we have alternating voltage. Again, first thing you do is when you get a graph, look at the axis. Here it is current, here it is time. Current in amperes, time in milliseconds. Similarly, here you have voltage, here you have time. Now this is also sinusoidal because it's the shape of a sine wave. Okay, so if you have alternating current, you will get alternating voltage. And alternating current, you know, the generator produces alternating current. Alternating current is produced in power stations by large generators like those shown in figure 29.3. This is a generator. Over here we have one. Generators in the generating hall of a large power station. And also you have previously learned about the generator. A generator consists of a coil rotating in a magnetic field. An EMF is induced in the coil according to the laws of electromagnetic induction. I had already taught this to you before. What happens is we have an electromagnet, and that the electromagnet is inside the generator. So the electromagnet, in an electromagnet you can turn on the on or off the magnetic field. So if you turn on the electromagnet, there is a magnetic field around that electromagnet. Now what happens is, in the generator, when the axle of the generator is connected to the turbine, so when the turbine turns, the axle in the generator is turned. So when the axle inside the generator turns, there it is connected to the electromagnet. So the electromagnet turns. Now we switch on the electromagnet, so there are magnetic field around the electromagnet. Now when the electromagnet turns, the magnetic field lines around that electromagnet will cut a coil of wire. There are coils of wire around the around this electromagnet inside the generator. So when a magnetic field cuts a coil of wire, you will have an induced voltage, and if it's in a complete circuit, you will get an induced current. Why we say complete circuit is because there can be an induced voltage even if the circuit there's a gap or when the circuit is open, but the current cannot flow when there is a gap. It has to be a complete circuit for the current flow. So the voltage is induced, but the current is induced when there is a complete path for the current to flow. Okay, a generator consists of a coil rotating in a magnetic field, and EMF is induced in the coil according to the laws of electromagnetic induction. This EMF V varies sinusoidally, like this. This is the induced EMF, an alternating voltage. And so we can write an equation to represent it, which has the same form as the equation for alternating current. Now, in the case of alternating current, you had I equals I naught sine omega t. Again, like I said, this omega t should be in a bracket. When you are entering in the calculator, don't enter it without the bracket, because the calculator will take sine omega and then multiply the result of that by t if you didn't use a bracket. But if you use the bracket, the calculator first will take the product of this omega t and then take the sine of that. So remember to use a bracket after the sine and put omega t inside that bracket. Okay, where V naught is the peak value of the voltage. Previously I naught was the peak value of the alternating current. Here V naught is the peak value of the voltage. We can also represent this graphically as shown in figure 29.4. Okay, make sure you answer all these questions. You can see again this equation is in this form. So V naught will be 300, omega will be 100 pi. Okay, then measuring voltage and frequency using the oscilloscope. This is the other topic. Then under oscilloscopes, we have two types of oscilloscope. The traditional cathode-ray oscilloscope, c.r.o, uses an electron beam, and the alternative is the digital oscilloscope, which is likely to be much more compact and which can store data and display the traces later. Let's learn how to take measurements using an oscilloscope. A c.r.o is an electron beam tube, cathode ray oscilloscope, electron beam tube, as shown in figure 27.4, page 424. We saw this earlier. Let's anyway have a look at it, page 400. Okay, let's have a look at the diagram, page 424. Yeah, so this is what we have. We learned this earlier. Yeah, so if you're not familiar with this, you can watch the video where I already explained this. Okay, so we'll go back to where we were. Okay, so yeah, so is an electron beam tube. Now you saw the electron beam tube that was in page 424, figure 27.4, but with an extra set of parallel plates to produce a horizontal electric field at right angles to the beam, figure 29.5. Okay, so here we have it, figure 29.5. Now in the electron beam tube, you had only one set or one pair of parallel plates, but in the cathode ray oscilloscope you have two, so you can deflect it this way as well as this way. So it means you can deflect it horizontally. The electron beam can be deflected horizontally as well as vertically. Again, I think you know how this works. You have the heated cathode which emits the electrons. Okay, here it's a filament metal, so when you heat the metal, what happens is it will emit electrons. Then this is the anode. it is positively charged, this is negative, so the electrons are attracted towards this, and what happens is it passes through this anode, and that's why it's called the electron gun, because it emits electrons. Then the electron is deflected towards the positively charged plate. So we have two plates here, one is positively charged, one is negatively charged. Negative and positive attract, therefore the electron gets attracted to the positively charged plate and is repelled by the negatively charged plate, because negative and negative repel. Cathode rays are also called beams of electrons, and they are produced in the electron gun and then deflected by the electric fields before they strike the screen. The electric fields are uniform because they are fields formed by parallel plates. Here we have parallel, these two plates are parallel, these two plates are parallel. So the electric field is there between them, and there is a uniform electric field between them. Then what happens is, when these electron beams hit the screen of the cathode ray oscilloscope, it produces a small spot of light. If you look at the screen and slow the movement down, you can see the spot moves from left to right, while the applied signal moves the spot up and down. When the spot reaches the right side of the screen, it flies back very quickly and waits for the next cycle of the signal to start before moving to the right once again. In this way, the signal displayed as a signal is displayed as a stationary trace on the screen. There may be many controls on a cathode ray oscilloscope, even more than those on the c.r.o. or cathode ray oscilloscope, illustrated in figure 29.6. You can see figure 29.6 here. Now these are the main ones that you need to know. Okay, see the controls, this, yeah, that's what you need to know basically, this one and this one. And you can also download these, there are some apps for cathode ray oscilloscope. You can download those to your Android or iPhone, and you can start using those so that you get familiar with the cathode ray oscilloscope. Alright, we also have to learn how to take readings from this. You have learned it anyway already in the O-level class. Here are the controls. The X shift and the Y shift controls move the whole trace in the X direction and the Y direction respectively. As I told you, you can try downloading one of those oscilloscope apps, and you can turn this and see how the shape of the wave changes. So you may see that the wave is stretched or in horizontally direction or in the vertical direction. And this is brightness and focus, but these two are the two important ones, the rim base control and the Y gain control. This changes the shape of the graph in the Y or vertical direction. This changes the shape of the wave in the horizontal direction. So you can adjust the settings so that you see more waves here or you see less waves here using this. But using this, you can change the heights of the heights and depths of the troughs and the crests of the wave. Okay, and here we have the on off button. Okay, so let's go through this part quickly. Okay, so here the X shift and the Y shift controls move the whole trace in the X direction and the Y direction respectively. The two controls that you must know about are the time base and the Y gain or Y sensitivity. Okay, so here Y input, time base, Y gain, X shift. Okay, so that is this one. Okay, here it's the Y shift, that is to move the whole trace up or down. But with this time base and Y gain, you can, like I said, stretch it in the X direction and the Y direction. See, they tell you that The two controls that you must know are the time base and the Y gain or Y sensitivity. This is called the Y sensitivity also. You can see in figure 29.6 that the time base control has units marked alongside. Okay, units marked alongside. Okay, if you look at a real one, you would be able to see that figure 29.6 that the time base control has unit marks alongside. Let us suppose that this reads 5 milliseconds per centimeter, though it might be 5 milliseconds per division. This shows that 1 centimeter or 1 division on the x-axis represents 5 milliseconds. So here is one of the settings that is for the index direction. Okay, the time base control. Okay, so 1 centimeter can be equivalent to 5 milliseconds, so you can adjust it. All right, so 1 centimeter is 1 division, we can say. This shows that 1 centimeter or 1 division on the x-axis represents 5 milliseconds. Varying the time base control alters the speed with which the spot moves across the screen. If the time base is changed from 1 to 1 millisecond per centimeter, so here you can see 5 milliseconds per centimeter. Here we have 1 millisecond per centimeter. You can adjust it so that you see more or lesser number of waves on the screen or on this grid over here, and that will make it easy for us to do the calculations. Once you have it proper number of suitable number of waves showing on that grid, you can easily take the calculations. Then the spot moves faster and each centimeter represents a smaller time, because in 1 millisecond for 1 centimeter, here 5 milliseconds for 1 centimeter. The Y gain control has a unit marked in volts per centimeter. So in the x-axis direction it is in milliseconds, in the y-axis direction the unit is volts. Okay, so you see 1 centimeter can be a certain number of volts, for example 5 volts per centimeter, or sometimes volts per division. If the actual marking is 5 volts per centimeter, then each centimeter on the y-axis represents 5 volts in the applied signal. It is important to remember that the x-axis represents time and the y-axis represents voltage. So remember this, very easy. Okay, so let's do a question using a trace from the cathode-ray oscilloscope. If you look at the CRO trace shown in figure 29.7, this one, you can see that the amplitude of the waveform is 2 centimeters and the distance along the x-axis for one complete wave is 4 centimeters. So you can see each division or each square is 1 centimeter by 1 centimeter. So the amplitude of this is 2 squares, which is 2 centimeters. Okay, so 2 centimeters. And for one whole wave, when you go like this, 1, 2, 3, 4, 4 centimeters. 4 centimeters, okay, in the x-axis direction. That's what they say here. Now, if your setting is such that if the Y gain or Y sensitivity, that is this setting, you will adjust it so that it is 2 volts per centimeter, then since the height of the crest is 2 centimeters, that means the amplitude will be 4 volts. So the highest voltage is 2 into 4. So 2 volts per centimeter is the setting that you adjust it to. But you know then it is 2 centimeters high. So that means it is 4 volts. Because 2 volts for 1 centimeter, then if it is 2 centimeters, it will be 4 volts. If the time base setting is 5 milliseconds per centimeter, so in this direction, 1 square is 5 milliseconds. So we have 1, 2, 3, 4, 4 squares. So then 4 squares is the time for one complete wave. 4 squares is equivalent to 20 milliseconds. So the period of the wave, so this is the time for one complete wave, 4 squares. So the period of the wave is 20 milliseconds. Since the x-axis measures time, the cathode-ray oscilloscope trace can be used to measure frequency. In the above example, period is equal to 1 over frequency. So this is how you find the frequency. Now you know frequency is 1 over period, then you found the period already, that is 20 milliseconds or 0.020 seconds. When you convert milliseconds to seconds, then you will get 50 Hertz. A c.r.o trace when a sinusoidal alternating current is applied to the Y plates. Sinusoidal alternating current applied to the Y plates. Okay, so again, make sure you answer all these questions. Again, very important. It's not only about the explanation. You have to answer the questions to have a better understanding of the chapter. All right, we'll move to the next page. Power and alternating current. Right, we'll go through this quickly. We use mains electricity to supply us with energy. If the current and voltage are varying all the time, does this mean that the power is varying all the time too? Yes. The answer to this is yes. So if the voltage is varying and if the current is varying, the power is also varying. You may have noticed that some fluorescent lamps flicker continuously, especially if you observe them out of the corner of your eye. A tungsten filament would flicker too, but the frequency of the mains has been chosen so that the filament does not have time to cool down noticeably between peaks in the supply. Now when it is alternating current, you have seen the peaks and the troughs, so it's varying. That means the power also should vary, but you will not see that over here in the filament lamp, because the frequency of the mains has been chosen so that the filament does not have time to cool down noticeably between peaks in the supply. Then comparing AC and DC. Okay, so let's go through this bit also. Again, the root mean square. Let's go through the root mean square values. This is again very important. I don't think you have learned this in the O-level class. So we'll go through it in detail, but it's very short. Root mean square values. There is a mathematical relationship between the peak value V0 of the alternating voltage and a DC voltage which delivers the same average electrical power. The DC voltage is about 70% of V0. So we have V, which is the voltage. Then again we have in the equation we use I for the current, V for the voltage, but V0 and I0 are the peak values of the voltage and the current respectively. Okay, so the note of the alternate mathematical relationship between the peak value V0 of the alternating voltage and the DC voltage which delivers the same average electrical power. The DC voltage is about 70% of V0. Okay, so DC voltage is about 70% of V0. You might have expected it to be about half, but it is more than this because of the shape of the sine graph. This steady DC voltage is known as the root mean square or r.m.s value of the alternating voltage. I think you have seen this briefly in the O-level class, but you didn't go into much detail. Remember seeing a graph somewhere in the Cambridge O-level book. Okay, let's have a look here. This is the one. Okay, so it's around 70% of that value. You see the oscilloscope trace from the experiment shown in figure 29.7. Alright, let's see. You might have, okay, so this steady DC voltage is known as the root mean square r.m.s value of the alternating voltage. In the same way, we can think of the root mean square value of an alternating current. So root mean square value we have for so we have it for voltage and also we have it for current. Okay, root mean square value of an alternating current, r.m.s. Again, the definition very important. The root mean square value of an alternating current is that steady current which delivers the same average power as the AC to a resistive load. So you are comparing the steady current with the AC. So alternating is the steady current which delivers the same average power as the AC to a resistive load. Okay, again over here you can see V0 of the alternating voltage, the peak value V0 of the alternating voltage, and a DC voltage which delivers the same average electrical power. Alright, so this equation explains everything. The lamps in box 29.2 are the resistive loads. Here, this has a resistance, this has a resistance. The lamps have a resistance, we call those resistive loads. A full analysis, which we will come to shortly, shows that r.m.s is related to I0 by this equation. And you can see that this is about 70%. We already learned that r.m.s is equal to 70% of I0, the peak value. Here the DC voltage is about 70% of V0. Similarly, we can apply it for the current also. So 70% of this I0 is equal to this 0.707. If you convert it to a percentage, it will be 70%. So this r.m.s is 70% of I0. Okay, so this is important equation. Okay, so r.m.s is equal to I0 divided by square root of 2. And note that this factor only applies to sinusoidal alternating currents. Okay, let's go through this one. Because power supplied by an alternating current is varying all the time, we need to have some way of describing the average power which is being supplied. To do this, we compare an alternating current with a direct current and try to find the direct current that applies the same average power as the alternating current. So here is the important point. To find the to do this, we compare an alternating current with a direct current and try to find the direct current. Okay, direct current. So here this line is a straight line and it is horizontal, so that means the current is not varying. Here the current is alternating. Okay, so to describe the average power, we compare an alternating current with a direct current and try to find the direct current that supplies the same average power as the alternating current. So this line represents the current, the direct current that supplies the same power as this alternating current. Figure 29.8 shows how this can be done in practice. Two lamps are placed side by side. One is connected to an AC supply on the right. Okay, so here we have the AC supply. Okay, you have seen this when you did the paper 3 practicals also. We used this kind of power supply. So we can adjust it to have AC or DC. So here we have it set to AC. One is connected to an AC supply on the right and the other to a DC supply. The batteries on the left. You know, batteries give out direct current. The AC supply is adjusted so that the two lamps are equally bright, indicating that the two supplies are providing energy at the same rate. Power is equal to energy over time. So the brightness depends on the power. The greater the power supplied to the lamp, the brighter the lamp will glow. When both have the same brightness, we can say that the power supplied by the DC power supply is equal to the power supplied by the AC power supply. So the AC supply is adjusted so that the two lamps are equally bright, indicating that the two supplies are providing energy at the same average rate. The output voltages are then compared on the double beam oscilloscope. And here we get the trace. A typical trace is shown in figure 29.9. This shows that the AC trace sometimes rises above the steady DC trace and sometimes falls below it. You can see this is the AC, this is the DC, direct current. This is alternating current. Okay, so direct voltage and alternating voltage. This makes sense. Sometimes the AC is delivering more power than the DC and sometimes less, but the average is the same for both. Okay, so again, make sure you answer all these questions. We have already seen these equations in the O-level class also. I think you have learned. And remember this, you first had the equation P equals VI. We had P equals VI and we had V equals IR. So using P equals VI and V equals IR, we got these other two equations. So you substitute, you know the equation P equals VI, and you also know the equation V equals IR. If you substitute V equals IR into P equals IB for V, you get, so this is V equals IR, you get, then when you substitute for V, you get I squared R. So V equals IR, substitute for V, then you get I squared R. And then also if you substitute for I, okay, V equals IR, then I equals V over R. If you substitute for I, you get V squared over R. So that's how you get this equation and this equation. But this one, we use it for the power dissipated. Now, for example, let's say in a cable, you would see that later. Okay, the cable has a resistance. So if there's a certain current flowing through that cable with the resistance R, we can find the power dissipated in that cable. So for that, we use this equation. And that is what they are also telling us here. To calculate the average power dissipated in a resistor, we can use the usual formula for power. We can use these equations. Now that is for a resistor. Remember that it is essential to use the r.m.s values of I and V, as in worked example 1. If you use peak values, answer will be too great by a factor of 2, because you remember it was this equation. I.r.m.s equals I naught over square root of 2. Where does the factor of 2 come from? Recall that r.m.s and peak values are related by I naught equals 2 times I r.m.s. So if you calculate I squared R using I naught squared instead of I r.m.s, you will introduce a factor, this one, that is a factor 2. There was a square root here, right? So if you square it, then 2 I r.m.s squared I squared. Yeah. So if you use, if you calculate I squared R using I naught instead of I r.m.s, you will introduce this. So the same is true if you calculate power using V naught instead of V r.m.s. It follows that for a sinusoidal alternating current, peak power is twice average power. And to help you understand this better, there is an example. Let's go through this so it will clear any doubts you have over here. A sinusoidal potential difference of peak value 25 volts, so V naught is 25, is connected across a 20 ohm resistor. What is the average power dissipated in the resistor? Now this is the peak value. You can't use that in this equation. Over here we had the equations. So we have V, we have R. Now you might think, okay, you can directly substitute and get the power. But remember, they tell you over here that you are not supposed to use the peak value, because if you use peak value, your answer will be too great by a factor of 2. So you have to use the r.m.s value. See, the importance of r.m.s values is that they allow us to apply equations from our study of direct current to situations where the current is alternating. Okay, so let's go through this equation. First thing is you find v.r.m.s, and that is equal to v0 over square root of 2, just like what you had for the equation of the I.r.m.s. I.r.m.s is equal to I0 divided by square root of 2. Similarly, v.r.m.s is equal to v0 divided by square root of 2. So first you find this. Now you have v0 is the peak value or peak voltage, that is 25. Square root over square root of 2, you get this. Then 17.7 you can substitute into this, then you will get this. Note that if we had used v0 rather than v.r.m.s, we would have found p equals 25 squared over 20, 31.3, which is double the correct answer. You see, this is double this one, approximately. Okay, so again, answer all these questions. Okay, the next topic, explaining root mean square. Okay, so we'll see how origin of the term root mean square and show the factor square root 2 comes about. You have already learned this equation, P equals I squared R, tells us that the power P is proportional to the square of the current I. P is proportional to I squared when R is constant. R is the resistance, we can say it's constant, the resistance of the component or resistor, we can say. Figure 29.10 shows how we can calculate I squared for an alternating current. So we'll learn that the current I varies sinusoidally. Why? Because it's alternating current, and during half of each cycle it is negative. I already explained that half the time the current is positive, half the time the current is negative. However, I squared is always positive, so if you square this I, it will become I squared. Because it's a square, the whole thing I squared will always be positive, because the square of a negative number is positive. Notice that I squared varies up and down, and that it has twice the frequency of the current. Okay, I squared, here is the graph, and you can see yeah, so you will have this. Okay, this is I versus T, and here we have I squared versus T. Okay, I squared is always positive because the square of a negative number is positive. Notice that I squared varies up and down, and that it has twice the frequency of the current. Now if we consider I squared this thing, so this is the average. Now remember, when you were learning about ideal gases, you learned the root mean square speed. There also, when you were learning root mean means average. So there, when you had that average root mean square speed, you had this sign like the less than and greater than sign. You had this, that is used to indicate the average. So the average mean value, or average also called the mean value of I squared, we find that its value is half the peak value. Okay, so here is the value. Because the graph peak value of I squared, we find that its value is half the peak value because the graph is symmetrical. Okay, now so again, now if we consider I squared, the average mean value of I squared, okay, so I squared, this thing means average. So now if we consider the mean value of I squared, we find that its value is half the peak value because the graph is symmetrical. You can see that over here. So if you get the average of this, it will be this one. Okay, time axis, this one. Now this is always positive, So above this one, and here we have I squared. I think this 0 I think is a mistake. Okay, so imagine it's not there, then you can, I think the 0 should be moved here. This 0 should be over here. This is the time axis, so this should be over here. Maybe it's corrected in your books, you can have a look. Alright, so again this is important. So the 0 over here should be written here, cross this 0 out from here and write it there. And you can see, now if this was 2 and here it was 1, here it's 0. So 0, let's say 1, 2. Then if you take half of 2, that is 1, which is this one, right? So here we can say I squared, the mean value of I squared is half the value of I squared. So that's what they say here. Now if we consider I squared, the average, if we consider I squared, which is this one I squared with this, which is the average mean value of I squared, we find that its value is half the peak value, because the graph is symmetrical. Okay, to find the RMS value of I, we now take the square root of I squared. So see, RMS, root mean square. Now this is the mean square value, because mean and also there is a square. So just like what you learned under ideal gases, we are doing something over here. So to find the RMS value of I, we now take the square root of this whole thing. This introduces a factor of the square root of half, which is 1 over square root of 2. So when you take square root of both sides, what will happen is this will become I RMS is equal to, this is the peak value. Okay, I naught, again it's better if there was a naught here written. Okay, so then this will be I naught divided by square root of 2, which is the equation that you saw earlier, which is this one. Okay, so this is, they are explaining the derivation over here. Okay, so then you get that equation. Summarizing this process, to find the RMS value of the current, we find root of mean of the square of the current, hence RMS. So you're getting the root mean square, RMS, because you have here the square, you take the root. So that's why you say root mean square, just like what you learned under ideal gases. You learned the root mean square speed there. Okay, then the next topic. Alright, so why use AC for electricity supply? There are several reasons for preferring alternating voltages for a national electricity supply system. First one, most important reason is that AC can be transformed to high voltages. So you can note those points down, or or maybe even number these. Most important one is that AC can be transformed to high voltages so that the current flowing is reduced. Now this is in the case of the transformer, the AC can be transformed or stepped up or even stepped down to high or low. In this case, if you say step up, it is transformed to high voltage. Step down means it's transformed to low voltage. So using a transformer we can do that, but with direct current we can do that. Okay, and also we learned this one, P equals VI. So if you want the same amount of power, you can increase the voltage and reduce the current. P equals VI. So if you increase V, you can reduce I to get the same amount of power. So what we do is so that the current flowing is reduced. So when we have lower current and when you transmit it, less power or energy lost as heat, and this leads to less power losses in the transmission lines. Transmission means you send it from one place to another. So from the electricity power station to your home, it has to travel through those cables. So that is the transmission process. Typically, the generators at a power station produce electrical power at a voltage of 25 kilovolts. This is transformed to a voltage of perhaps 400 kilovolts. In the O-level class also you have learned this. A step-up transformer is used at the power station to increase the voltage. Now for example over here from 25 kilovolts to 400 kilovolts, and as much as 1 megavolt in some countries. The power is then transmitted along many kilometers of high voltage power lines. Figure 29.11. You can see that here. So here is the power station. You use a step-up transformer to increase the voltage from 25 kilovolts to 400 kilovolts, and then it is transmitted at that high voltage through these cables. Power lines carry electricity from power station to consumer. So that's what I told you, the example from the power station to your home, where you are the consumer. The home is the consumer. Power lines before being transformed down to a lower voltage. So once it comes to your house, there is a near your house on to your neighborhood, there is a step down transformer, because it is at 1 megavolt. So this has to be reduced. So it can not just one, it can undergo several stepping downs at several transformers. So maybe for a factory they will need more than 220 or 230 volts. So at the area where there is a factory, there is a step down transformer to reduce it to a voltage which is much more than what the voltage we use in our homes. And then again it is stepped down, or maybe it can also be directly stepped down to 230 or 230 volts here. The power is then transmitted along many kilometers of high voltage before being transformed down to a low voltage for supply to the millions of consumers. The transformers used for increasing and decreasing the voltage are discussed in detail in the next section. The high voltage brings problems. The lines must be suspended high above the ground between pylons. Okay, so what you have here, now we can't really see it, those are the pylons. Okay, so between pylons, and high quality insulators are needed to prevent current passing from the cables to the pylons. Okay, as current flows, now you can see the cable here. The cable is fitted between two pylons over here. All right, you can really see that in the picture because it's too small. So you would have seen something like a circular disc. Next time you go outside, you have a look at this. Okay, you can have a close look. There is something like a round disc, like something like a it's something like a pot, let's say, but filled. Okay, so you have something like this. It's a shape, a certain shape, like a pot kind of shape. Those are the pylons. So the cable is on top of that. And high quality insulators are needed to prevent current passing from the cables to the pylons. As current flows through the transmission lines wires, it loses power because of the resistance of the lines, and we can calculate this using the equation P equals I squared R if you know the resistance of the cables or lines, transmission lines, wires, cables. The wires become warm. This is resistive or ohmic heating. Now we can find the power loss using again the equation P equals I squared R. As discussed in chapter 9, the smaller the current, the smaller the losses, because P equals I squared R. R is constant. So if you can reduce I, you can reduce P, the power loss. So the power loss equals I squared R. R is constant, that is the resistance of the cable or the lines or the wires. So to reduce the power loss, you can reduce the current. That's why we transmit at high voltages and low currents. This is illustrated in worked example 2. Okay, so to help you understand this better, let's go through this example. A power station generates electrical power at a rate of 10 megawatt. This is the power. This power is to be transmitted along cables whose total resistance is 10 ohms. Now they are giving the resistance of the cable. Calculate the power loss in the cable if the power is transmitted at 50 kilovolts and at 250 kilovolts. Now they have given you the power. They have given you the resistance, they have given you the voltage. So let's find that. Something that students confuse is this. Okay, so this power should not be used, because this is the electrical power that is given. So once this the power, the electricity is sent to the cable from the power station, the power there is 10 megawatts. Okay, so when the power station, at the power station, the power is 10 megawatts. Alright, this power is to be transmitted along cables whose resistance is 10 ohms. So we have to use the 10 ohms, and this P equals VI. We can use also, we can use P equals V squared over R, or P equals I squared R. So there are three equations, but we are given the resistance. So we'll find the, first we'll find the current. Now using this equation P equals VI, we can find the current. Now I told you that equation, this is what we use to calculate the power loss in the cable, because this is the equation that has the R. P equals VI doesn't have R now, and also P equals V squared, that has a R, but this is what we are using. Okay, so here we have this one. Now first, when it is 50 kilovolts, we can find the current 200 amperes to get the same amount of power. Okay, so this we are not using over here. This is the power that is given in the beginning from the power station. But what happens is, at the receiving end, at the consumer end, you will not have this power. You will have lesser power, because certain amount of power, so that is either this or this, is lost during the transmission process. So this is the power that is input at the transmission from the power station, but when the electricity is passing through the cable, energy is lost. So either this amount or this amount is lost. So this minus either this or this will give you the power at the consumer end. Okay, so we are using this value. Now we find the current. We use this value and we find the current. Now the power is the same in both cases. The power that is input or sent from the power station. Now you can see the current here is much higher, the current here is much lower compared to this. Okay, then P equals I squared R. I is 200, R is 10. Okay, so this is very simple. We have P equals I squared R. Now you can see when the current is higher, when it is 200, the power dissipated or the power loss is 400 kilowatt. So P equals I squared R. When I is 40 amperes and R is still the same, 10, then the power loss is only 16 kilowatts. So you see, when the current is more, the power loss is more. When the current is less, the power loss is less. See, then P, the total power being transmitted. Now again you can see this is a mistake students make, that's why they say take care. Then 10 megawatt, that is the total power being transmitted, and over here this P is the power lost in the wires. Notice that using a higher voltage does not change the resistance of the cables. So at a higher voltage we can reduce the current and give the same power. We have shown that by increasing the voltage by a factor of 5, we have reduced the power loss by a factor of 25. Increasing the voltage by a factor of 5. So 50 times 5 is this. So 50 is 100, 200, yeah, 200. So if you multiply this by 5, you get this 50 times 5, 250. And if you do that, what happens is the power loss is reduced by a factor of 25. Okay, so divide this by 25, you would get this 400 divided by 25 is 16. You can try it with your calculator. And so again, explanation. The resistive heating of power lines is a waste of money in two ways. Firstly, it costs money to generate power because of the fuel needed. Secondly, more power stations are required, and power stations are expensive. The use of transformers to transform power to high voltages saves a few % of the national bill for electrical power and means that fewer expensive power stations are needed. It is claimed that having a few very large power stations gives economies of scale. but this is debated by many environmentalists who would prefer to see many small local power stations. It is also the case that new developments in technology are making it easier to transform direct current to high voltages. This is more compatible with sustainable electricity generating systems such as photovoltaic solar cells. So we may see the development of DC grid systems in the near future. Okay, that's the end of that topic. And one more point is, like I mentioned before, if you want to find the power at the consumer end, you can subtract. Okay, so 10 megawatt minus, let's say if it was this one, minus 16 kilowatt will give you the power at the consumer end, because this is the total power that is supplied. Okay, you can see they also mentioned here total power that is transmitted, and when this is transmitted along the cable, it loses this much power. So what you have is in the end 10 megawatt minus 16 kilowatt. The next topic is transformers. You have learned this in the O-level class also. There are different shapes for the transformers. Okay, so many different configurations are possible with different shapes of core and with the coils wound separately or one on top of the other. So you can also have a transformer just a single iron core. Okay, so you can imagine something like a long rod, a thick rod. Okay, and then you will have the primary coil here, and down here you will have the secondary coil just on one. That is also possible, but what we see most of the time is this. So you can even have one iron core in the shape of a barrel, and on the top there are some coils, and at the bottom there are more coils, so in the shape of a cylinder, and that is also a transformer. That's why they say many different configurations are possible with different shapes of core and with the coils wound separately, like over here, or one on top of the other, like what I told you. The potential difference, now by the way, this is the input coil, also called the primary coil. So if we say P, primary coil for letter P for primary, then VP, IP. Similarly, secondary coil, VS, IS, NS. Number of turns in the secondary coil, voltage in the secondary coil, current in the secondary coil. We can also call this the input coil. Then you have to use NI, VI, I. And here this will then be the output coil. So NO, VO, IO, then O for output. So some books, some papers say primary coil, some papers say input coil, like that. So you have to know both names. And if you asked to draw the magnetic field in here, you will have to draw it like this. All the magnetic field lines pass through the iron core. So let's say we have magnetic field like this. Now here you can use the right hand grip rule, okay, for solenoids. So you have a north pole there, and yeah, so if you have a north pole here and a south pole here, the magnetic field lines will be going like that. Okay, so all the magnetic field lines should be inside this. You shouldn't have anything out of the iron core, because of the iron core only all the magnetic field lines are passing through it. That strengthens the magnetic field that is passing through this. So that's how it becomes more efficient. Okay, so if you didn't have this, the magnetic field lines would be like this, out of this. Not all of them will pass through this, but once you have the iron core, all the magnetic field lines produced by this pass through this. Okay, so north pole here, south pole here, magnetic field lines go like this, and then like that. Okay, so then what will happen is here you have south pole, here you have north pole, induced. Okay, so as a result the current will flow like this. You can try it with the right hand grip rule for solenoids. Here it is induced current and induced voltage. See, so when you have this, okay, input, this produces an alternating magnetic field in the soft iron core. The second coil, now again, you know, this won't work with DC, it works with AC. So for this moment the current is flowing this way, then another moment the current is flowing the other way, then the magnetic poles are reversed, everything is reversed here. The secondary this produces alternating magnetic field in the soft iron core. The secondary coil is thus in a changing magnetic field, and an alternating current Is is induced in it. There is thus an alternating EMF Vs across the secondary coil. Defining quantities for a simple iron core transformer. Here we use a soft magnetic material, because if you use a hard magnetic material, it will be permanently magnetized. Now when you switch this off, there is no induced voltage or induced current here, because this core loses its magnetism, because it's a soft magnetic material. Iron, mu metal, those are soft magnetic materials. See, no electrical connection between the primary and the secondary coil. Okay, here it's all insulated, so here nothing. Energy is transferred from one to the other via the magnetic field in the core. See, iron core. So here you don't have current flowing like this and then this way to this. No, this is all insulating. Okay, here you have iron core. The magnetic field lines pass through this. And I already explained to you about the step up and step down transformer. Step up transformer increases the voltage, step down transformer decreases the voltage, and here is the equation. So you can also write this as Vp over Vs equals Np over Ns. So the ratio of the turns is equal to the ratio of the voltages respectively. You can also write Ns over Np equals Vs over Vp. Ratio of the voltages, you can say, is equal to the ratio of the corresponding turns in the coils. Okay, so already you have learned this formula. Say we have 5 turns producing magnetic flux. Over here you can see 1, 2, 3, 4, 5. So there are 5 turns. 1, 2, 3, 4, 5. Here you have 1, 2, 3, 4, 5, 6, 7, 8. How many? 3. Is it 9 or 10? Okay, we'll see this. Yeah, here it's 10. Okay, there are 10 turns. So what will happen is, now since the ratio of the voltages is equal to the ratio of the turns, this will double. The voltage will double. Okay. Yeah, so here you have less turns, here you have more turns, means the voltage will be increased. So here if you have 5 turns, here 10 turns, their number of turns is double. So the voltage also will be double. We have 5 turns producing magnetic flux. The flux links the 10 turns to the secondary coil. Because flux linkage is N phi is proportional to the number of turns. See, it follows that there is more magnetic flux, twice as much, linking the secondary coil than the primary. As the magnetic flux changes, because we are using alternating voltages, the EMF induced in the secondary coil is greater than the voltage in primary coil. Okay, so I already explained all this. So what will happen is the voltage will also double. So imagine here it's 50 volts, then here it will be 100 volts. If it was 1 volt, it will be, on the secondary coil, it will be 2 volts. So that's what is explained over here. Now this is a step up transformer. Here we have a step down transformer. Here the number of coils is more than the number of coils here. So the voltage here will be less, more than the voltage here. So that means it's a step down transformer. B is a step down transformer. Alright, make sure you answer all these questions. Here is an example to help you understand it better. A radio requires 6 volt supply but has to be operated from a 230 volt main supply. You can see these details if you look at the back of an electrical appliance. They have the power rating, the voltage that is required, and when you connect an appliance to the mains is supplying 230, but that appliance uses a much lesser voltage. So we will have a step down transformer inside the appliance or in that cable to reduce the voltage to the voltage required for that appliance. It is fitted with a transformer to reduce the mains voltage. Calculate the turns ratio for this transformer if the primary coil has 5000 turns. Now you can see the voltage is reduced from 230 to 6 volts. That means if the primary coil has 5000 turns, the secondary coil, which is the coil in the appliance, on the appliance side, coil on the appliance side, has to have a lesser number of turns, because here 200, it's reduced to 6. 5000 has to be reduced in proportion. That's why if the primary coil has 5000 turns, how many turns must the secondary have? Okay. So we have ns over np. Then you can use this formula. Vs over Vp equals ns over np. Then ns over np equals Vs over Vp. Either way you can write it. And write it in the way that is easier for you. Now in this case we are supposed to find ns. So we write ns over np equals, then if we start with ns, we have to start here with Vs. So 6 over 230, np 5000. Okay, so 5000, and you multiply, you will get if you multiply by 10,000, you will get 260, 130, right? Yes. Okay, so in the secondary coil it should have 130. Okay, so here is a image or diagram of a transformer. You have seen the transformers. Even if you look at certain lamp posts, like they have fixed the transformers there, and also on the ground you have transformers. You should be able to see it when you walk around in the streets. Okay, so then the next equation is this one. The power in the primary coil, P equals VI, is equal to the power in the secondary coil. So P for primary, S for secondary, and if you rearrange it, you will get this. So you may have to find the number of turns or the voltage, and then you may also have to find the power. Always the power in the primary coil is equal to the power in the secondary coil. So if you know the power in one coil, it's equal to the power in the other coil, because we assume it is 100% efficient. And by the way, here it's not a ratio like what you see here, because this is Vs over Vp. Here it's starting with Ip over Is, so it's the inverse. So don't compare this with the other one. Okay, there the ratio of the turns is equal to the ratio of the corresponding voltages, but that is not the case here. Here the power in the primary coil is equal to power in the secondary, so don't confuse it with this one. I will go through this bit also. Already I explained this one. Note that this relationship assumes no power is lost in the transformer. I told you we assume it's 100% efficient for this to happen, for this equation to be true. In practice, some power is lost because of the resistance of the transformer coil windings. So the windings become warm. In addition, the changing magnetic flux can induce currents in the core. The eddy currents, these are called eddy currents. These eddy currents hit the core because of its resistance. Large transformers, such as the one shown in figure 29.14, you can see it's like this. You see the shape here. Why they have it is, we'll see. Handle large amounts of power. A small percentage is wasted, and the resulting heat is carried away by the cooling fluid pumped around the transformer and through the fins, which are visible in the photograph. So it has fins like this to let out that heat, otherwise it will get heated up. Okay, so around this there can be this cooling fluid pumped around, so that it carries away heat from these fins. The transformers used in electricity supply industry must be designed with a great care to minimize energy losses. So that's why we assume it's 100%. So because they have designed it such that the loss is very little. The electricity supply may pass through as many as 10 transformers between the generator and the consumer. If each transformer wasted just 1% of the power, that would give an overall loss of 10%, because it passes through 10 transformers. In each transformer, if there is 1% loss, then there will be a 10% loss in total. Since there are roughly 100 big power stations in the UK, that would require 10 power stations just to cope with the losses in transformers. Today's well-designed transformers have losses of under 0.1%. This contributes greatly to energy savings in the power transmission industry. So they have designed the transformers so that they are very, very efficient, meaning the power loss is under 0.1%. So it's about 99%, 99.9% efficient. Okay. So answer all these questions, you may have to use this formula and this one. So under transformers there are only two formulae. This one, the ratio of the turns is equal to the ratio of the corresponding voltages, and the power in the primary coil is equal to the power in the secondary coil, and power equals VI. So substitute with this. Okay, so those are the two equations that you have to know under transformers. The next topic is rectification. Okay, under this we already, when I was explaining the summary and the beginning of the chapter, I went through this, so we'll go through it a bit faster. Many electrical appliances work with alternating current. Some, like electric heaters, will work equally well with AC or DC. However, there are many appliances such as electronic equipment which require direct current. For these, the alternating mains must be converted to DC by the process rectification. So the process of converting AC to DC is rectification. Again, you can see this word is in green bold letters, which means you have to know the meaning, and also the meaning is given in the glossary. We can go to the glossary and look for the word rectification. So KLMNOPQ REC here. No. Yeah, the process of converting alternating current AC into direct current DC. Okay. A simple way to do this is to use a diode, which is a component that will only allow current to flow in one direction. Since shows a circuit for doing this together with a graph to show the effect, you will see that the output voltage is always positive, but it goes up and down. This is technically direct current because the current only flows in one direction. So here you get direct current because there is no negative voltage, only the voltage is in one direction. Similarly, the current is only in one direction. Even though it's changing, it's still direct current and direct voltage, current in one direction. Okay, so you have to know half wave rectification and full wave rectification. For the full wave rectification, you use a diode bridge. 4 diodes are used like this. I told you how it works. Okay, then in this one, for half the time, the voltage is 0. This means that the power available from a half wave rectified supply is reduced. For half of the time the voltage is 0, and this means that the power available from a half wave rectified supply is reduced. Half wave, yes, yeah. So it's only available for half the time, so the power is reduced. And to overcome this problem, we use the bridge rectifier. To overcome this bridge rectifier, this consists of 4. Now what happens is, here half the time the power is 0, right? But here during the entire time it is there. See, here it's 0, but here it's there. So that is the advantage. So that's how we get rid of this problem. Then you can construct a bridge rectifier using light emitting diodes. Now I already explained this, I'm not going to explain it again. At the beginning of the video I already explained it. Okay, you can use LEDs which light up when current flows through them. By connecting this bridge to slow alternating current supply to a slow, for instance 1 Hz from a signal generator, you can see the sequence in which the diodes conduct during the rectification. So you can see at one time it is these 2 diodes light up, the other time these 2 diodes light up. This way you can see the direction that the current is flowing. That's what is explained here. This part I already had explained to you. And the last topic is smoothing. Now you have bumps here. We want to get rid of those bumps. So in order to produce steady direct current, now here also it's DC, but it is bumpy. We can produce steady direct current, and that is by the process of smoothing. For this we will use capacitors. In order to produce steady DC from the bumpy DC that results from rectification, a smoothing capacitor must be incorporated in the circuit in parallel with the load resistor R. Again you saw that here the resistor, load resistor R, here it is there. So we can connect a capacitor in parallel with the load resistor, and then what happens is this. Okay, this is the last bit. A smoothing capacitor must be incorporated in the circuit in parallel with the load resistor. Remember, it has to be parallel. This is shown in figure 29.18. A smoothing capacitor is connected across in parallel with the load resistor. The idea is that the capacitor charges up and maintains the voltage at a high level. It is discharged gradually when the rectified voltage drops, but the voltage soon rises again and the capacitor charges up again. The result is an output voltage with ripple. So this is what you get. Now what happens is the capacitor gets charged, and then what happens is when the current is flowing the other way, capacitor charges up and maintains the voltage at high level. It discharges gradually when the rectified voltage drops. Okay, so the current, what happens is the current can only flow in one direction through the diode. So it goes like this, and when it goes, it charges the capacitor. Now when the current tries to flow the other way, what happens is the capacitor, it won't flow the other way through this side. It won't flow, not this side, it won't flow the other way. So when it doesn't flow the other way, what happens is the capacitor starts discharging. Okay, so the capacitor starts giving out the charge, so then that will flow this way. So when half the time when the current is not flowing from the supply, there is a flow of current from the capacitor through this resistor. So that is what corresponds to this part here. So in the beginning the current is flowing, and then half the time, that is over here, the current is not flowing. This time the capacitor is charging. Here you see the capacitor is discharging. So that is the time the V out. Okay, this is the voltage across the load resistor. So this part over here is when the capacitor is discharging. This part over here is when the capacitor is charging. Capacitor charges up and maintains the voltage at high level. It discharges gradually when the rectified voltage drops, but the voltage soon rises again and the capacitor charges up again. The result is an output voltage with ripple. So you see, like a ripple. The amount of ripple can be controlled by careful choice of the values of C and R, capacitance and the resistance. A large capacitor discharges more slowly than a small capacitor, so will give less ripple. Similarly, if R has a large value, C will discharge more slowly. When you learn about capacitors, you learn that when greater this resistance R, the longer it will take to discharge. Lesser the resistance R, the quickly it will discharge. Under capacitors, you have learned this in detail. In practice, the greater the value of quantity RC, the smoother the rectified AC. So again, a larger capacitor discharges more slowly than a smaller capacitor, so will give less ripple. Similarly, if R has a large value, so if you have a large value for R, then it takes the resistance is more, it takes a longer time for the charges to flow. That means it will take a longer time to discharge. So this is charges to flow means from the capacitor. Okay, so it takes a longer time for the capacitor to discharge. So if you have greater value of R and a greater value of C, what will happen is the smoother it will be the rectified alternating current. However, if R and C have large values, it will be difficult to change the value of voltage quickly. However, if R and C have large values, it will be difficult to change the value of voltage quickly. Note that in figure 29.15 and 29.18, here 29.18, 29.15 is this one. We have represented the load on the supply by the load resistor R. This represents any components that are connected to the supply. For example, R could be replaced by a mobile phone battery that is being charged, or by one of the electronic circuits discussed in chapter 25. All right, again, make sure you answer all these questions. We can briefly go through the question here. Number 18, a bridge rectifier circuit is used to rectify an alternating current through a resistor R. A smoothing capacitor C is connected across R. Figure 29.20 shows how the current varies. You can see that over here. Use sketches to show the changes you would expect if R is increased, if C is increased. Now if R and C are increased, what will happen is the smoother the rectified AC. However, R and C have large values. If R and C have large, it will be difficult to change the value of the voltage quickly. Let's have a look at the solution or answer to the question. If R is increased, less pronounced ripple. If C is decreased, more pronounced ripple. Okay, so less pronounced ripple, more pronounced ripple, something like that. Less ripple. You know the ripples that you get when you throw a stone in the water. So more pronounced ripple means it will have like more, it looks more bumpy. Less pronounced means those bumps are low. It's not as sharp ripples. Okay, less pronounced ripples. Okay, so we have this. This question is also, I think, a good question. Sketch the following voltage patterns. Sinusoidal alternating voltage. We can have a look at the solution. This one. Then same voltage but half wave rectified. Half wave is this. You have seen that over here also. Half wave rectified. It's because it's alternating. Then the same voltage as B but smoothed. So you will get this. See, this is the top of the crest, so that corresponds to this part. Top of this corresponds to this part. So once it is smoothed, this graph becomes this one. Okay, you don't need to draw the parts here. This and this you can just erase it. They have drawn it to show you what is happening. So this was the original graph, what I'm showing. What you see here, this is the original graph. So they are still having the original graph and showing you the new graph so that you can compare. Actually, if it is not there, it's easier to understand, but when it is there, you can compare it. That's why. So this is what you get. Okay, the result of this being smooth is this one. Okay, so without these bottom parts here, but they are drawing that to show you what is happening. Okay, so let's have a look here. This is what you get. So when you smooth this, you get this one. The same voltage as A but full wave rectified. If it's full wave rectified, it should be this one. So in part D you get this. Now part E, the same voltage as D, that is the full wave rectified one, smoothed means it will be like this. Now again, if you look closely, you can see this is the peak. Here is a peak, so that corresponds to this, and over here this corresponds to this. Now over here what you will have is 1 2 3 4. So 1, okay, which corresponds to this. 2, this corresponds to that. 3 corresponds to this, and this is the 4th one, corresponds to that. So that's what you are getting. I think you are able to answer this question. It's based on what you learned here. Yeah, and go through this part again so that you understand it better, and go through these questions again. Now again we have the summary. We'll go through it again. So just to review, this is the equation, very important one you learned, and then the second one for which has r.m.s, and remember you can use like this: v.r.m.s equals v0 over square root of 2. You have to know the meaning of this. Root means square value of an alternating current is that steady current which delivers the same average power as alternating current to a resistive load for a so that's it. Okay, then for a sinusoidal AC you get this, and I naught omega angular frequency I naught is the peak value of current. You have to know all this. This we learned about the transmission. step up transformer, step down we learned. Then the two equations under transformers, very important. If this is 100% efficient, then you get this. And about rectification and smoothing. In rectification we use diode, okay, half wave one diode. Then full wave rectification, bridge of 4 diodes. You have to know the arrangement. They can ask you to draw it. Okay, there was a past paper question where you had to draw this one. Okay, so you have to know the directions. Like this, it goes like this, this, and if it's flowing this way, it goes like this, like this, like this. So the directions of these are important. See, all are pointing to the right. You can remember it that way. See, this diode is pointing to the right, this is pointing to the right, this is pointing to the right, this is also pointing to the right. Bridge of 4 diodes. Then capacitor is used for smoothing. Capacitor smooths the rectified voltage. So it has to be rectified first, and then only it is you have smoothing. Now again we can check the glossary for the meaning of this word smoothing to help you understand it better. Let's check that in the glossary. Smoothing, right? Let's see whether it is there. P, Q, R, S, L, M, E, F, G, H, I. Oh yeah, it's not there. Yeah, that word is not there, but you have it here. Okay. Smoothing capacitor must be incorporated in the circuit, so that is to reduce, in order to produce steady DC from bumpy DC that results from rectification. A smoothing capacitor must be incorporated in the circuit in parallel with the load resistor R. Okay, so that's the end of the chapter. Make sure you answer all these questions in the brown boxes and check the solutions. All the solutions are here. And also do the end of chapter questions after doing the self-assessment or the questions in the brown boxes. Check the solutions to these also. These are like the past paper questions, but the self-assessment questions are like questions based on the theory. So it will make sure that you have understood the theory well when you do those self-assessment questions or the questions in the brown boxes. Okay, that's the end of the lesson on alternating currents.